Give a large language model a complex task. Now, clear the memory and give it the exact same task again. Do it a third time. The puzzle pieces are the same, but the final assembly varies every time. To solve this, developers rely on two standard methods to guide the model: few-shot prompting, which provides examples, and chain-of-thought prompting, which asks the model to show its work. These techniques are the industry standard for a reason. They reduce ambiguity in the prompt and force the model to break down complex logic into digestible steps. Mapping these techniques reveals a flaw. This matrix plots output quality against output variance. Standard zero-shot prompting sits in the bottom left, consistently low quality. Apply few-shot or chain-of-thought, quality improves up the y-axis, but fractures across the x-axis. Better, but unreliable. This happens because there is a vast mechanical difference between heavily suggesting a direction and explicitly constraining a system. Prompting is a suggestion. By feeding an AI more context and demanding deeper reasoning, you are effectively giving the model more variables to juggle. More variables create new vectors for unpredictable behavior. To build reliable systems, we have to look under the hood and dissect the mechanical flaws of both few-shot and chain-of-thought prompting. A high-quality answer that you cannot reliably reproduce is useless in a rigid, real-world production environment. Let's start with the internal mechanics of few-shot prompting. This 2D plane illustrates how few-shot anchoring works. Instead of simply issuing instructions, you provide specific input-output pairs. These examples form a boundary box. The model observes the structure of the examples and learns to replicate them, operating safely within provided guidelines. But pattern imitation does not mean the model actually comprehends the underlying logic. It is merely mimicking the surface geometry of the data. Because of this, microscopic changes in the examples, a different word choice, or a minor shift in tone will alter the model's downstream reasoning style. Even with a strict, consistent set of examples, the model can still fail. It might latch on to the wrong element of your examples, simply because multiple valid interpretations of that pattern exist. The real danger arrives with an edge case. What happens when user input falls slightly outside the exact parameters of your examples? The model attempts to apply a rigid pattern to a novel situation. The logic breaks, and the output becomes immediately erratic. Forced to improvise without a relevant anchor, the model's performance destabilizes. Few-shot prompting creates the illusion of a boundary. In reality, it leaves the system exposed the moment it faces unpredictable user input. Chain-of-thought prompting attempts to solve complex problems differently, by forcing the model to articulate its intermediate steps before delivering a final answer. For complex math, for logic puzzles, and structured decision-making, breaking the problem down reduces the chance of the model taking a shallow shortcut. But the assumption that forcing an AI to think step by step creates a predictable thought process is mathematically flawed. Demanding more reasoning does not guarantee consistent reasoning. To see why, look at this decision tree. This represents the intended path of chain of thought, a clean progression from start to finish. But instructing a model to think step by step places zero constraints on which intermediate steps it takes. This is an unbounded solution space. There are no rules governing how detailed the model should be or what specific logical principles it must apply at each juncture. Give the model a prompt, and it weaves one specific path through the network. Run it a second time, and it traces a different route to get to an answer. Different internal reasoning paths inevitably yield different final outputs. Chain of thought increases the model's verbosity and its path variability. It produces a detailed output, but it fails to align that logic with the developer's intended outcome. This variability creates a severe operational risk when deploying chain of thought in a production setting. Consider an early-stage failure in the model's logic. One early step in the reasoning process contains a minor error. Because the model is instructed to follow its own steps, the subsequent logic steps build directly on top of that flawed foundation. The instruction that was supposed to increase accuracy mathematically guarantees the initial error will be amplified as the model moves forward. The final output generated by this corrupted process creates a silent failure point. It is highly detailed, convincing, and factually incorrect. A standard AI hallucination is often easy to spot. A cascading failure produced by chain of thought is hidden by paragraphs of seemingly sound logic, making it much harder for engineers to detect. Chain of thought weaponizes the model's own processing power against it, turning isolated miscalculations into systemic failures. Looking at both the few-shot boundary box and the chain of thought decision tree side by side reveals their shared limitation. Few-shot prompting successfully helps the model understand format. Chain of thought successfully helps the model think deeply. But neither technique physically restricts the available solution space. In commercial deployment, a good answer is functionally useless if it is not a repeatable answer. The business requires exact precision every single time. Bridging the gap between high intelligence and high reliability cannot be solved by editing text in a prompt. It requires strict architectural control. You must build an environment that physically clamps down on the model's available choices, stripping away its ability to wander. This is where AI-Gagi comes in. It serves as an overarching control framework designed specifically to enforce these constraints. Rather than relying on the model to interpret suggestions, AI-Gagi operates by enforcing a consistent, predetermined logical path that the model cannot deviate from. Deploying reliable AI means abandoning the hope that writing better instructions will eventually yield total control. It won't. Mastering large language models means building the unbreakable track the logic is forced to follow.